So let's just go through a few more examples of how climate has varied through these various marine isotope stages. This is just another comparison of two marine isotope stages, MIS6 up here and MIS42 down here. So this went on from essentially about 200,000 years to 138,000 years or so before it deglaciated and then went into the last ice age that peaked in 21,000 years ago. So the idea is to again compare to the other MIS stages to see how ice volume in meters of sea level equivalent and various other quantities that are compared. So comparison of MIS42 records, blue and lower axis, and MIS6 red, and the upper time scale is given here and here. LR04 benthic isotope stack, so it's just where the data comes from. And B, estimates of total Eurasian thin line and North American dashed line ice volumes. So you can see that the ice volume over North America didn't change dramatically. Northern American changes were not as dramatic as changes of ice volume over Europe, Eurasia in general. Again, potentially related to thermohaline circulation changes and so on. So modeling is done typically to try to understand such details, and there are other dynamics involved like this. So if you look at the interaction of the glacier with bedrocks, for example, 48,000 years ago, this is a height of 4.5 kilometers of glacier at its maximum here. So advanced position of the glacier depresses the sill here. So if you zoom in, you can see that the glacier has crossed over to this slope on this side of this sill, and the ocean forcing is low here in terms of degree centigrade that affects the glacier melt at the edges, for example. By 47.8 kilo years, the glacier subsurface warming has created a glacier retreat, and if you zoom in, the glacier line has gone on this side of the slope of the sill. So once this happens and the forcing by the ocean increases because of this retreat here, then the melting accelerates, and by 47.5 kilo years the rapid retreat occurs, and the ocean forcing has now increased to about 1 degree centigrade and has gone all the way across down the slope here. Such mechanisms are still playing out in Antarctica, for example, because the glacial melt at the bottom begins to have frictional melting, and the rheology and sliding of the glacier and the accelerated rapid retreats begin to happen. So retreated position, elevated sill by 47.4 kilo years has gone way back here. So the channel has opened up and the lobe has go back is down here. So you can see now the ocean forcing is again retreated back to here, and it has become less here in terms of amount of heat being supplied to the edge of the glacier. So as you can imagine, if there is still cooling happening globally, then this can begin to advance again. So the grounding line where the glacier is attached at its front end can shift based on such detailed mechanisms. I just wanted to give you a sense of just how complicated it is to go back in time and reconstruct these things and understand the differences between various marine isotope stages. So looking now the impact on other parts of Eurasia, for example, looking at Lake Baikal's biogenic silica, which corresponds to productivity and temperatures. So here we are looking at relatively speaking, warm temperatures and cold temperatures. So going back from about 70,000 years ago again, you have the variations in biogenic silica corresponding to changes in temperature and lake productivity. Again, you see some ups and downs in terms of climate change. And if you look at Central Asia annual precipitation in millimeters, they correspond to very wet times and relatively dry times. So you can see again the rapid fluctuations in the amount of rainfall, which would have serious impact on settlements, resources, and so on for the Homo species which were wandering around at this time in Asia. East Asian monsoon annual precipitation also shows similar variability, but now the numbers are much higher here. This is below 330 millimeter at its peak, whereas here this is in the range of almost 600 millimeters, because monsoon regions typically had a lot of rain. So whether this favored the earlier spreading of the Homo species into Asia as compared to Europe, for example, has to be understood in these contexts, because associated with these will be changes in vegetation, desert areas, temperatures, and so on. So this is the Kyrgyz Tian Shan glaciation piecemeal through these wet and dry, cold and warm periods. This is the Altai glaciations. This is the Grain Taklamakan desert that appeared and disappeared. So these are the time periods in terms of the human technology and behavior and so on, expertise. Upper Paleolithic core and flake technology here, Middle Paleolithic. So basically we are going through MIS 4, 3, 2 and 1. Okay, so by this time we are already deglaciated into the Holocene, which we will look at a little bit more detail later in this chapter. But these signatures were not so uniform in the tropics. So this is a figure that shows quaternary glaciations and glacial chronologies over Africa. So here you have where quaternary glaciations were evident, where they were unlikely, and they were equivocal. So evidence is not very clear. So Atlas Mountains here here. So this is a circle, so glaciation was evident. Tibesti, again unlikely here. A lot of these are unlikely, whereas these were evident glacial signatures. This was equivocal as far as evidence is concerned. So Tibesti, Jebel Mara, Ethiopian highlands, East African mountains, Mountain Cameroon, and Drakensberg here. So you can see that the evidence is based on the altitude. Glaciation happened or didn't happen, or the evidence is not very clear. So in other words, in the crucial place where hominin migrations in and out were happening over these periods, we don't have a very good handle on how glaciation would have affected vegetation, temperatures, rainfall, humidity, and also species migrations, non-human species migrations, or human impact on the non-human species, for example. Glacial chronology, existing and lacking. So here we are talking about, again, Simien Mountains, Arsi Mountains, Bale Mountains. So where there is existing evidence and where there is lacking evidence. East African mountains here. So I just wanted to make a point that while high latitude, the glaciation, deglaciation, meridional overturning impacts on vegetation, ice extent, and so on are fairly clear, in the tropics, signal is quite complicated based on the orography and other factors. Okay, so this is a reconstruction now to look at ice extent, land ice extent during MIS 650 to 135,000 years ago. So land ice extent during MIS 6 based on recent proxy and field data-based global digital glaciation ice extent compilation of Ehlers and Gibbard, land ice extent used in the MI6 equilibrium climate simulation. So using this kind of distribution, again, models like UVIC are run to see other changes in meridional overturning and ITCZ and monsoon strengths and so on and so forth. Okay, so these models typically don't simulate land ice. Even most of the recent IPCC class models didn't have land ice, they only had sea ice. So modeling land ice is beginning now, but it's not a easy task. Example of modeling here, atmospheric surface specific humidity anomaly for 116,000 years ago relative to 1800 AD, so beginning of the Industrial Revolution, let's say. Figure shows simulated surface specific humidity was higher 116,000 years ago than AD 1800 in the equatorial regions. So positive numbers means it was much warmer, much more humid here 116,000 years ago than the pre-industrial period, and lower across the northern hemisphere all the way here. So we are obviously in the thick of the glaciation here, but we may be in the stadial or interstadial depending on which MIS it was, but nonetheless the high latitudes were much drier in terms of kilograms water per kilograms of air, but the tropics were much warmer and much more humid. And remember that the relative humidity, the humidity and temperature relation is exponential, so small temperature changes would have produced large humidity differences. 1 degree warming produces a 7% change in 7% increase in humidity. Similarly here, 114,000 years ago minus 1800 and 106,000 years ago minus 1800. These are precipitations including snow in water equivalent difference in both cases. So you can see the 114,000 years ago as compared to 116,000 years ago. If it's warm and humid, you can expect more rain, so be careful of the color scale here. Here blue is more rain and drier here, where there are cold and drier cold temperatures and drier humidities. And 116,000 years ago is much more complicated here, so it's raining more here, including snow equivalent in water, and drier here, red colors, and it is wetter across here, but not deep in the tropics, but mostly in kind of West African, Indian, East Asian monsoon, and maybe US, southern half of the US, and so on. But this is from a model, so one has to be careful. Global average precipitation anomaly for 114,000 years ago and 106,000 years ago relative to AD 1800. Global average precipitation derived from 122,000 year time series climate simulation performed on the UVIC Earth system model that we talked about before. Okay, so again, we need models to fill in the gaps that are left by the sparse data we get, just to see what would have been the drivers of human migrations and speciation. Okay, so I'll leave it here and come back and talk about another mode called the bipolar seesaw mode, which also was a critical player potentially, because the carbon cycle and methane we talked about before being not similar to each other potentially is related to this, because when the northern hemisphere is cold, southern hemisphere is warm, and vice versa, and the northern hemisphere has much more land, so the impacts on carbon cycle versus methane would have been very different in these cases when you have warm north, cold south, or vice versa. Okay, so let's come back to that in the next podcast.